All right, so next we're moving on to mathematical induction. Now, the principle of mathematical induction is a method for proving that statements involving n, the set of natural numbers, 1, 2, 3, 4. So you're talking about you're talking about the counting numbers or positive integers or the set of whole numbers are true for all natural numbers. The procedure for a proof by mathematical induction is as follows. 1, verify that when n is equal to 1, the statement is true. Step 2, assume that the statement is true for n is equal to k. Step 3, we're going to show that the statement is true for n is equal to k plus 1 using the statement in step 2. So in other words, we're going to use 2 to prove that the statement, to prove that 3 is true. Then when step 3 has been completed, it is stated that the statement is true for all positive integers n, which is an element of the set of what? Natural numbers. Let us see how induction works. When the statement is true for n is equal to 1, then according to step 3, it is also true for n is equal to 2. Because step 3 says if it's true for n, step 3 says if it's true for k, it's true for k plus 1. So if it's true for n, it's true for what? N plus 1. So if it's true for 1, it will be true for 2. If it's true for 2, it's true for 3. So that implies it will be true for n is equal to 3, which implies it will be true for n is equal to 4, and so on. It will be true for every natural. All right, I'm skipping 19. I'll get back to it. I'm going to do 20. Now, example 20 says, prove by mathematical induction that the sum of the squares of the first n natural numbers is equal to n into n plus 1 multiplied by 2n plus 1, all divided by 6. So the first thing I'm going to do is the statement I'm being asked to prove, I'm going to call that statement Pn. So Pn is the statement that from r is equal to 1 to n of r squared. Now I'm going to expand this statement for clarity. This is equal to 1 squared plus 2 squared plus 3 squared plus, and this is going down, and we're doing all this all the way to n squared. The series is the sigma representation of the series when expanded of the series, the sum from r is equal to 1 to n of r squared. When you expand that, it's what? 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, all the way down to what? N squared, whatever n is. And this, according to the statement, is equal to n into n plus 1 multiplied by 2n plus 1, all over 6. Now, the first thing we're going to do is show that the statement is true when n is equal to 1. So we're going to say when n is equal to 1, we're going to get P1. On the left-hand side, when n is 1, that's what the first term, the sum. When n is 1, it's simply saying the sum of the square of the first what? Counting number. So that would just be what? 1 squared. This is the left-hand side. Now, on the right-hand side, we would have what? When n is 1, we have 1 multiplied by 1 plus 1. N is 1. 2 times 1 plus 1 all over 6. And this is the right-hand side. On the left, 1 square is 1. On the right, we have 1 times 2. 2 plus 1. 2 ones is 2. 2 plus 1 is 3. Times 3 all over 6. Up top, we're going to have 6 over 6, which is also equal to what? 1. So when n is equal to 1, the left-hand side and the right-hand side of my statement are both equal. So the statement is true when n is equal to 1. So I can make that declaration that Pn is true when n is equal to 1. This is step 1. Now, of my proof by mathematical induction, step 2. In step 2, we're going to assume that the statement is true when n is equal to k. So when n is equal to k, we get pk, which is the statement. Remember, no, we're just replacing n with k. From 1 to k of r squared, which essentially is what? 1 square plus 2 square plus 3 square plus, and this time we're not going to n, we're just simply going to what? K squared, replacing n with k. And this would be equal to k multiplied by k plus 1 multiplied by 2 times k plus 1 all over 6. We assume that this statement is true. So this assumption is part of the solution. I'm assuming that this statement is true. Now, the third thing we're going to do now, the third thing is that I'm now required to prove that pk plus 1, so now n is k plus 1, which is asking me to sum the square of the counting numbers from r is equal to 1 to r is equal to k plus 1 of r squared, which is equal to 1 squared plus 2 squared plus 3 squared plus k squared plus k plus 1 squared. So pk, or pk, which is the summation of r squared from r is equal to 1 to k, is asking me to square the counting numbers from, to sum the square of the counting numbers from 1 to k. pk plus 1 is asking me to sum the square of the counting numbers from 1 to k plus 1. So k plus 1 comes immediately after k. So it's going to be 1 square plus 2 square plus 3 square up to k square, and then I have to go to what? K plus 1 square. And over to the right now, I'm going to replace n with k plus 1. So I'm going to have k plus 1 multiplied by k plus 1 plus 1 multiplied by 2 k plus 1 plus 1 all over 6. We need to simplify the right-hand side. Make life easier. K plus 1. This is k plus 2. Over to the right, we have what? 2k plus 2 distributive law, plus 1. This is still over 6. And this simplifies to what? K plus 1 multiplied by K plus 2 multiplied by 2K plus 3 all over 6. This is what we have to prove. Now, how are we going to do that? Essentially, we're going to take the left-hand side and work it until we get the right-hand side. What is the left-hand side? The left-hand side is this. From R is equal to 1 to K plus 1 of R squared, which is 1 squared plus 2 squared plus 3 squared, all the way up to what? K squared, then up to what? K plus 1 squared. 1 squared is the first term, 2 squared is the second term, 3 squared is the third term, K squared is the K term, and K plus 1 squared is the K plus 1 term. This is the left-hand side. We must work the left-hand side until it becomes the right-hand side. This is the right-hand side. Now, if you're observant, you'll notice that the sum of the square of the counting numbers from 1 square to K square is actually PK. It's actually this. That this part here is actually this. And from step 2, we're told that this is equal to K multiplied by K plus 1 multiplied by, we assume that this is equal to this. We did that at step 2. We're going to assume that that is true. And so we're going to take out all of this and put K into K plus 1 into 2K plus 1 all over 6 plus K plus 1 square. You put this over 1. Remember, our objective is to work it until it looks exactly like the right-hand side. Well, I'm going to start by making this into one fraction. If you're adding or subtracting fractions and the denominators are different, you must find the LCM, which is 6. 6 into 6 is 1. 1 times the numerator, and we get K into K plus 1 multiplied by 2K plus 1 plus 1 into 6 is 6. 6 times the numerator, which is K plus 1 squared. We're still working the left-hand side. The objective is for it to become the right-hand side. That's step 3, to prove that the left side is equal to the right side. Next, I'm going to factor out the common factor. The common factor is K plus 1. If I factor out K plus 1, I'm going to get K plus 1. When I factor it out to the left, I'm going to be left with K into 2K plus 1. When I factor out K plus 1 to the right, I'm going to get 6 into K plus 1. And remember, this is still over 6. Now we have what? K plus 1 over 6. Over to the right, we have what? 2K squared plus K plus 6K plus 6. We still have K plus 1 over 6 into 2K squared plus 7K plus 6. And now the last thing we need to do is to factorize 2k square plus 2k plus 6. Now, I'm going to do it by trial and error. I'm guessing the method you all are most familiar with is the trial and error method. I'm factorizing. I'm going to have 2k here. I'm going to have k here. When I multiply 2k by k, I'm going to get 2k squared. I'm going to have, let me say 3 here and 2 here. As I said, it's trial and error. Let me see if this will work. 3k plus 4k. 3 plus 4k is 7k. So this will work. And this is my answer. Remember, we were working the left side for it to become the right side. Let's look at the right side now and see if it's the same thing. K plus 1 multiplied by k plus 2 multiplied by 2k plus 3 all over 6. As you can see, it's the same thing. So that ends step 3. Now that step 3 is finished, you're going to make a statement. And this statement is step 4. The statement is the same statement every single time you make it. That pk plus 1 is true when pk is true. Therefore, Pn, which is the statement, the sum from r is equal to 1 to n of r squared is equal to n into n plus 1 times 2n plus 1 all over 6 is true for all n, which is an element of the set of natural numbers.